In this video, we're going to talk about matrix equations and how they relate to systems of equations. So we've looked at systems of equations before, particularly in relation to matrices. So we represented them using an augmented matrix. So remember, that was a square matrix, typically a square matrix, combined with a constant matrix. It essentially represented the system. We drew a line where the equal signs were. We were able to put it into the calculator, reduce the matrix, and that was a method for solving our system of equations. We can also represent a system of equations with a matrix equation. So when we use an augmented matrix, the variables go away. We don't have any more variables. We just have the constants in the problem. A matrix equation is actually a little bit different. So it's going to be an actual equation. There's going to be an equal sign in it. There's also going to be variables in it. But what's in the equation, the individual parts of the equation, are actually going to be matrices. As it turns out, though, we can actually use the same original matrices we used for the augmented matrix. So with the augmented matrix, we had a coefficient matrix. It was all the coefficients for our variables. And then we also had a constant matrix, and that was everything on the other side of the equal sign. We can use those same parts. We just put them together in a different way in order to create a matrix equation. So for example, what have we done before versus what we're going to do now? So say this is our system of equations. So 3x1 minus 4x2 is equal to 1. That's our first equation. And then 2x1 plus x2 is equal to 5. That's our second equation. If we represented this as an augmented matrix, this would be the augmented matrix. So the first row represents the first equation. We just drop off our variables, keep our constants. Notice that 4 is negative because there's a subtraction in our equation. That vertical line represents the location of the equal sign, and then we have our constants on the other side of that. Second row is representative of the second equation. So this would be our augmented matrix. So we know how to put this into the calculator. We know how to reduce it with the calculator. We know how to interpret our solutions from there. Another option for representing the system of equations is as a matrix equation. So if I were to take the two parts of the augmented matrix and split them up and use them individually, I can create a matrix equation. So everything that's to the left of our vertical bar, representative of that equal sign, that's going to be a matrix that's on the left-hand side of this equal sign. The constant column, representative of everything that's to the right of the equal sign, is also going to be a column matrix to the right of the equal sign. What's different, though, is notice what I have next to that square matrix. I have a column matrix that contains my variables. In this case, we had the variable x1 and the variable x2. Well, what does this actually represent? Why does this matrix equation actually represent our system of equations? Well, this is actually a multiplication. Everything we have on the left-hand side of this matrix equation is a matrix multiplication, which we've already talked about. So I want to think about what would happen if we took all of this and we multiplied the left-hand side of this equation out. So this is a 2 by 2. This is a 2 by 1. Because those inner two dimensions are the same, we know that we can actually do this multiplication. What would it look like if we did this multiplication? Well, remember, we go across the row and then down the column, and that's going to give us what we add together to come up with something that results in our actual final matrix. So if we were to multiply these two parts together, we have 3 times x1. We have negative 4 times x2. We'd add those together. So 3x1 minus 4x2 is equal to the first element in that column matrix on the other side. So 3x1 minus 4x2 is equal to 1. Well, what's that? That's actually just our first equation over here. So what we did is we inadvertently represented this first equation in a more condensed form. Same thing happens if we use the bottom row. So 2 times x1 plus 1 times x2. So 2x1 plus x2 is equal to 5. Well, that's just our second equation. So this is just another way to represent our system of equations. Perhaps we want to include the variables. Perhaps it's helpful to know what the variables are. This is another way to represent that system of equations other than an augmented matrix that still uses matrices. So say we were to use the augmented matrix form. The procedure we use to simplify is called Gauss-Jordan elimination. We talked about how we would do this sort of indirectly in a calculator. But if we want to solve this form of the system, not the augmented matrix form, but the matrix equation form, if we want to solve this, in other words, determine what the values are for our variables, we use what we call the matrix inverse. So we'll talk about that in a minute. What does that look like? How do we find that? We're going to take this matrix, the square matrix, multiplied by our column matrix containing our variables. We're going to find what we call the inverse for that particular matrix. So this is dependent on a couple things. Number one, the system has to be consistent. Remember, that's just the word that means we can actually solve it. So in other words, using this particular technique for representing and solving a system is not going to work in cases where we have no solution. If there's no solution, that can't be determined using this technique we're going to talk about. Also, we have to make sure that the system has the same number of variables as equations. So notice this one has 2 variables and 2 equations. It would work if we had 3 variables, 3 equations, so on and so forth. But if those 2 numbers don't match, then this technique also will not work. So it's dependent on a little bit more. How do we know immediately from the matrix equation whether we're in the right situation? Well, the coefficient matrix is going to be a square matrix. So wherever it's a square matrix, the rows represent the number of equations, the columns represent the number of variables. So 2 equations, 2 variables, the numbers are the same, which means this technique is going to work. So how do we actually go about solving something like this? Well, I want to take something like this and sort of condense it down to what this looks like algebraically if we're just solving for a single variable in a single equation. So say we had something of the form AX is equal to B, which is essentially what we have here, just in matrix form. So we have A representative of a constant, B representative of a constant, and then of course X is our variable. So right now A and B look variable, but they're not. We're going to assume they're constant, we just don't know what they are at the moment. We can solve something like this in 2 different ways. Normally we use division, but we can also use what we call an inverse, and we're going to look at both of those. How does that actually look? So for instance, let's look at some actual numbers. Suppose our equation was 4x is equal to 9. In other words, we want to know what does x have to be to make that equation true. Well, if we were going to solve that in the standard way, we just use opposites. So 4 times x is equal to 9. If we wanted to eliminate the multiplication of 4, we just do the opposite. So the opposite of a multiplication by 4 is a division by 4. We know we have to keep things in balance in our equation by doing the same thing to both sides. So we eliminate our 4 by dividing a 4, but we balance it by dividing by 4 on the other side of the equation. The 4's reduce and our x is isolated, and whatever x is equal to at that point represents the solution to our equation. So based on this solution technique, we get that x is equal to 9/4. So that's going to be the solution to that equation. That's the standard method we would use to solve that equation, and it's perfectly correct. There's actually another way to essentially do the same thing, but make it look a little bit different. Use actually multiplication instead of division. So dividing by 4 is also the same thing as multiplying by 1/4. Those actually represent the same operation in the sense that they do the same thing to this particular kind of problem. So if we wanted to eliminate this 4, isolate our x by eliminating that 4, we could divide by 4, or alternatively, we could multiply by 1/4, multiply by what we call the multiplicative inverse of 4. So 4 and 1/4 are multiplicative inverses. Inverse just means opposite. So these are opposites from a standpoint of multiplication. In other words, if we multiply them together, they reduce down to 1. They cancel if we want to think of it that way. So we can multiply by 1/4, otherwise known as the reciprocal, the multiple inverse, the multiplicative inverse, the reciprocal, and then whatever we do on one side, we have to do on the other side as well. So we multiply by 1/4 on the left to eliminate the 4. We also multiply by 1/4 on the right to keep things in balance. Well, 9 times 1/4 ends up being 9/4. You can think of the 9 as a 9/1, if that helps, and then just multiply numerators and denominators straight across, or alternatively, just use your calculator at that point. Multiply those two together, and we end up with 9/4. Same answer, slightly different solution technique. Technically speaking, we're doing the same thing in both of these situations. We're just representing it here with multiplication, whereas here we're representing it with division. This technique is going to be very similar to what we're going to do for a problem that looks like this. Structurally, this problem and this problem are essentially the same. We've got something constant multiplied by something variable, and it's equal to another thing that's constant. Well, we have something constant multiplied by something variable, and it's equal to something else that's constant. Structurally, this is more complicated, but structurally, these are essentially the same thing. So this technique we've used right here, we're going to have a version of that to solve this kind of problem. Now, what we have to keep in mind, though, is that this technique to solve this kind of equation doesn't actually apply when we have matrices. So here we divided the 4 in order to eliminate the 4 that was multiplied by the x. We did things to both sides, and then the answer followed from there. There is no matrix division. So when we looked at matrix operations, we had addition, subtraction, 2 versions of multiplication, nothing involving division. That's because there is no such thing as matrix division. So dividing is not an option for a problem like this because there is no way to define division for matrices. So instead, what we're going to do is something that looks a little bit more like this. We're going to multiply by the inverse. Well, the inverse of 4 is 1/4. That's the multiplicative inverse. It's the reciprocal of 4. Here, 4 is basically the same thing as the square constant matrix up here. They represent essentially the same thing structurally speaking. So what we want to know is what is the inverse of this particular matrix, what we think of as sort of being the same thing as 4 from a structural standpoint. We're going to find what we call a matrix inverse. So again, we'll talk about that in just a minute. How do you actually find that? The good news is your calculator is going to be really, really helpful here. So we'll be able to use the calculator for that. So we're going to multiply by the matrix inverse, kind of like we did right here. We have a little bit more flexibility here, though, than we do in terms of the matrix equation. What do I mean here? Well, matrix multiplication is not commutative. We determined that A times B and B times A when we're talking about matrices. They're not always the same thing. And in a lot of cases, one multiplication is defined and the other one you can't even do, just based on how your matrices are structured. So we have to keep in mind that the order we multiply things in is going to matter. So we're going to take this matrix, let's think of this as the matrix A. We're going to take this matrix, we're going to find its inverse, kind of like we took 4 and found its inverse. Notice we took the thing we wanted to eliminate and we multiplied it by its inverse, and that's what eliminated it. Well, if we follow this particular model and applied it to matrices, we multiplied by the inverse on the left-hand side of the equation. We multiplied it on the right-hand side of the equation. So it would look like something like this in terms of our matrices. Multiply the inverse. This is the notation for inverse, A, with a superscript of -1. That's the inverse of the matrix A. Structurally speaking, this would be the same thing right here. This is not actually correct, though. Multiplying on the left on one side, multiplying on the right on one side, it works for numbers. It doesn't work for matrices because matrix multiplication is not commutative. The order we multiply the matrices in matters. So if we choose to multiply on the left for this particular side of the equation, which is what we're going to do, we're going to multiply on the left, then we have to multiply on the left side on the other side of the equation as well. So combining the two inverse matrices like this, multiplying on the left on one side, on the right on the other side, not actually correct. We have to keep things fully balanced, and we have to do the exact same operation on both sides. So if we multiply the inverse on the left on one side, we also have to multiply the inverse on the left on the other side of the equation. Other than that, it's essentially going to be the same thing as what we did right here. We just have to be a little bit more careful about our order, and determining what this inverse is going to be a little bit more involved than just taking 4 and relating it to 1/4. So let's look at an actual example about what this would actually look like. So we have the previous system, the one we just looked at. We want to solve it using the matrix inverse. In other words, solve the matrix equation. So here was our system. We converted it to a matrix equation. And so our goal is to solve this particular system of equations, okay? So we want to isolate what we're thinking of as the variable part. So this is the variable part right here. We want to isolate it. In other words, we want to get rid of this matrix. It's multiplied. So normally we think of just dividing to eliminate something. Well, we know there is no matrix division, so we can't divide out the matrix. Instead, what we want to find is the inverse of that matrix. So this matrix we want to eliminate, we want to find its inverse. Kind of like 4 and 1/4 eliminate, this matrix and its inverse will also eliminate one another and reduce, so that we can isolate this particular matrix right here, the matrix containing our variables. Okay, so this is our inverse. Well, where do you actually get that? How do you find something like this? First thing we want to do is take the graphing calculator, and we want to type in this matrix that we're trying to find the inverse for. So let's review how you would do that. So remember, we have the matrix menu, which is right here above the x to the -1 button in blue. So it says matrix right there. So second, x to the -1. And remember, we have 3 columns in the matrix menu. We have the name submenu, the math submenu, the edit submenu. I'm going to go to the edit submenu, and that's where I actually type in a matrix that I'm interested in. Doesn't matter which one you use. I'm just going to use matrix A. So I'm going to highlight it, press enter. I need to type in my dimensions. So matrix A is going to be a 2 by 2. So 2, enter, and it formats what I want. Now remember, as we type in the elements, it goes across the row and then down to the next row until you end up in the bottom right-hand corner. So I'm going to type in matrix A, which is 3, -4, and then 2, 1. So 3, enter, -4, enter, 2, enter, 1, enter. And notice once I fill it in, it tabs back up to the top element. I want to double check that this is exactly what I wanted to type in before I do anything else. So top row is 3 and -4. Bottom row is 2 and 1. So this looks good. This is the matrix I want. Once I have everything typed in, I can't clear to get out or delete to get out. I have to quit to get out. So second and mode is going to take me out of that menu. Now I have that matrix saved in the calculator under matrix A. Next thing I want to do now is go back in and use that matrix. So back into the matrix menu, second, x to the -1. Now when we do reduction, when we have an augmented matrix and we want to reduce, we use edit and then math and then names. The inverse operation, finding the inverse for a matrix, is not actually going to be under the math menu. It's actually going to be a button on the calculator. So I actually get to skip the math menu. I used edit. I'm skipping this menu. I can immediately just use the names menu and pull up the matrix I want. So I typed it in as matrix A. So I'm going to hit enter. I've highlighted it. I'm going to hit enter. It's going to bring it onto my home row. And then I want to find the inverse of this matrix. Now this is the notation for inverse. Inverse notation is a superscript of -1. And if you look at the button you use to access the matrix menu, it's X with a superscript of -1. This is actually the inverse button right here. This is actually the button we're going to use. So once we have that matrix on the home row and we want to find its inverse, we're going to use that matrix on the home row and then hit that superscript of -1. This means take that matrix as entered and find its inverse. That's what that's telling us to do. So once we have that typed in, we can hit enter, and it's going to give us the inverse. Now this looks awful. This looks awful because this is the decimal, this is the decimal version of our matrix inverse. So it's another matrix. It's actually the same size as the matrix we started with, but this is the decimal version. We can convert this to fractional version pretty easily. So I'm not going to type anything else in, but I'm going to go to the math menu. So right under alpha, it says math. I'm going to go to the math menu. First option, arrow frac, convert to fraction. So I'm going to highlight that, hit enter. And what this is saying is take the answer from the previous line, in this case, this matrix, and convert everything to fractional form. And then I'm going to hit enter. And that's going to give me a better version of my matrix. So it's actually the same matrix, but this is the version of that matrix where everything is in fractional form. So this is going to be the inverse of our matrix A. I'm going to write that down. So that's the inverse of matrix A. Think of this as the opposite matrix. If 4 and 1/4 are opposites, well, this matrix and this matrix are opposites as well, in the sense that if we multiply them together, they will reduce. They will essentially cancel one another out, just leaving us with the variable part that we're interested in. So I want to multiply this inverse matrix on both sides of the equation on the left. So just like with the constant multiplication we did over here at the very beginning, 4 was multiplied on the left by 1/4. We have to be consistent in ordering when we do this with matrices. So if I multiply a 1/4 on the left, the number on the other side of the equation has to be multiplied on the left as well. So I'm going to multiply by my inverse matrix on the left, and then the same thing on the other side of the equation. I'm multiplying by that inverse matrix on the left. On this particular side, because these two matrices are inverses, they reduce. Essentially, they reduce the same way that 1/4 and 4 reduce. We know that if you multiply 1/4 and 4, you get 1. We don't have to write the 1. A coefficient of 1 is just understood. So essentially that just isolates the x for us. Same kind of thing here. These two matrices reduce, and we're just left with the variable component of our problem. Now we have to do the same thing on the other side, and that's not negligible. We have to actually determine what that multiplication is going to be. So remember, across the row, down the column, across the row, down the column. So this is a 2 by 2 and a 2 by 1. So the result is going to be 2 by 1. Okay. Now we could go by hand, multiply the individual elements by hand. Notice that requires us doing some things with fractions. If you want to avoid that, there is another option as well, other than having to do this by hand. So if you kept everything in your calculator, you didn't clear anything, notice you still have that matrix right there. And what we want to do is we want to multiply that exact matrix by this column matrix that has a 1 and a 5. We can do this in the calculator. So if you go back into your matrix menu, so don't clear anything, leave your home row as it is, go back into the matrix menu. So second, x to the -1 in the matrix menu. Notice it still has matrix A. Now this is not the inverse, this is just A. We got the inverse using this button right here. What I want to do is I want to go to the edit menu and I want to type in this additional matrix that I have. My goal is to do this multiplication in the calculator, but if I'm going to do it in the calculator, I need to have this matrix in the calculator. So I'm going to go to the edit menu. I'm going to go to another matrix. Let's choose B. I'm going to hit enter. And now I want to type in this second matrix I need, which is a 2 by 1. So 2 rows, 1 column. And the matrix we want is 1, 5. Okay, so I have the matrix I want. I'm going to quit, get out of there. Again, do not clear anything. What we want to do is we want to take this matrix and multiply it by the matrix we just typed in. So if you take the matrix you currently have for the inverse and hit the multiply button, it brings in the answer from the previous line, which is the matrix we're interested in at the moment. And then we want to multiply it by that matrix we just typed in. So I'm going to go back into the matrix menu, I'm going to choose that additional matrix that I typed in, that 2 by 1 matrix, the 1 and 5. So I'm going to highlight it, I'm going to press enter. And what this now represents is the answer from the previous line, in other words, the inverse matrix, multiplied by this constant matrix that I just typed in. In other words, it represents the right-hand side of the equation, the part of the problem I'm attempting to reduce. So if I do that multiplication and then hit enter, it's going to give me the actual answer to my problem. So notice now this is in fractional form because we multiplied by something in fractional form. If for some reason this is in decimal form and you want to convert it, same thing as before. So you go to the math menu, arrow frac, and you can convert it to fractional form. So this is the result. This is the answer at the very end. We reduced everything on the left-hand side, isolated the variable component of our matrix equation, and whatever we're equal to at this point represents the actual solutions, the actual values for our variable pair in this case. So this is going to be our solution to the problem. So if we wanted to solve the original system of equations, we know that x1 is going to be 21 over 11 and x2 is going to be 13 over 11. We could also verify this using another solution technique. So if we created an augmented matrix, used the augmented matrix form into our calculator, reduced all of that, we would end up with the same answer at the end. This is just another option for how we could solve. Okay. So let's try another example. Let's look at one that's slightly bigger. So here's our next system. Now again, we could solve this using an augmented matrix. We could solve it using some other type of solution technique, maybe graphing, maybe substitution, something like that. We want to solve it using a matrix equation and matrix inverse methods. In other words, using that matrix inverse to cancel out some of the parts of our equation. So I have 3 variables in this case, 3 equations. I'm going to write the coefficient matrix, which is all the coefficients on the left-hand side of each equation. So we have a 1, a -1, and a 1 for our first row. Second row, second equation. Notice we don't have a term that has an x1, so that means in the x1 spot we're going to put a 0. Then we have a coefficient of 2, a coefficient of -1. And then our bottom row, we have an x1 and x2, we're missing an x3. So we have 2, 3, and 0. And then we have a column matrix representing those 3 variables. So again, if we were multiply across the row and down the column, we could regenerate those particular parts in our equations. And then all of that is equal to that column matrix on the right-hand side of the equal sign. In this case, each equation is equal to 1 on the right-hand side. So that's going to be the 3 by 1 column matrix consisting of all 1s. So this is going to be our matrix equation, same structure as the one we previously had, just a little bit bigger. So our goal is to isolate the variable component in our equation. In other words, we have to reduce this matrix so that this is isolated. We're using matrix inverse methods. In other words, we want to find the inverse of this particular matrix. We want to find the inverse so that we could multiply them together, just like we did above, and they would reduce and we'd isolate the variable component in our equation. If you were to type this equation in, or not equation, excuse me, matrix, type this matrix in the same way we did the other matrix. So we type it in, we save it, we use the inverse button, which is the same button we use to access the matrix menu. It's got that superscript of -1. This will be the inverse we get. So I recommend take a minute, pause it, type in this matrix, find your inverse, verify that this is what you get. Okay, so take a minute and do that. Once you have that this is your inverse, what are we doing? Well, we're taking this, we're multiplying it on the left-hand side on both of these sides of the equation. So left-hand side on the left, left-hand side on the right. Over here, when we multiply, those 2 matrices reduce and we isolate the variable component in our problem. On the other side, that's where we're actually determining the solution, the values of our variables. So that multiplication we actually have to do. Now again, you can do this in the calculator, or let's just see if we can do this one by hand. This one's not too bad because it doesn't have fractions the way the previous one did. So we have 3 times 1, which is 3, 3 times 1, which is 3, and then negative 1. So 3 plus 3 is 6, plus negative 1 is going to give us 5. So that's where that comes from. Okay, next row. Negative 2 times 1 is negative 2. Negative 2 times 1 is negative 2, and then 1 times 1 is 1. So negative 2 plus negative 2 is negative 4. Negative 4 plus 1 is negative 3. And then our bottom row. Negative 4 times 1 is negative 4. Negative 5 times 1 is negative 5. So negative 4 plus negative 5 is going to be negative 9. 2 times 1 is 2. So negative 9 plus 2 is going to be negative 7. So this is going to be the column matrix we end up with. 3 by 3 multiplied by a 3 by 1 gives us a 3 by 1. That's our result. And then those 3 multiplication and addition operations give us the actual values. So that means x1 is going to be 5, x2 is going to be negative 3, and x3 is going to be negative 7. Okay, let's look at one final example. It doesn't matter that the numbers are bigger. Here the numbers are bigger, which means in theory it's a good time to use the calculator to solve something like this. So we can write the coefficient matrix. Notice we have all 3 terms in all 3 equations, so we don't have to put in any zeros. 3 equations, 3 variables, which means our coefficient matrix is going to be 3 by 3. It also means our column matrices are going to be 3 elements each. So we write the matrix equation. The goal is to eliminate this particular matrix, isolating the variable matrix. So I need to find the inverse of this. I find my inverse. So take a minute, do that in your calculator, find your inverse. We're going to take this inverse. We're going to multiply it on both sides. So we find the inverse of this matrix, multiply it on both sides of the equation on the left. The inverse times the matrix reduces, leaving us with that variable column matrix. And then we have to do the multiplication on the other side. So inverse times column matrix. Take a minute and do that. So if you haven't already done that, pause it. Find the inverse matrix, and then we're multiplying the inverse matrix by this column matrix. What you end up with is going to be this particular matrix in decimal form. Now remember, if you have decimal form, you can convert to fractional form, which in general is preferable, using math, and then the convert to frac option, first option under the math menu. And this is going to be our column matrix. So take a minute with this one. Notice not as much is written out, but everything you need is written out. We're taking this matrix. The goal is to essentially cancel this out. So we take this matrix, find its inverse, multiply both sides of the equation by that inverse, which isolates the variable matrix. We multiply that inverse matrix and the column matrix on the right-hand side. This should be our result. We convert it to fraction. So x1 is going to be 91 over 5. x2 is going to be 279 over 10. And then x3 is going to be negative 76 over 5.